Hello and welcome to Physics Talk. Here we discuss various topics on physics and try to clear all your doubts. So come on, let us begin. I discussed some features of the nuclear force in the previous lecture. The conclusions were drawn by minutely analyzing the structures of the nuclei. In order to get further information, we take the smallest nucleus for simplicity as a case study. We know that the smallest nucleus belongs to hydrogen, but the most abundant isotope of hydrogen, called as protium, has only one proton at the center, and that serves as its nucleus. But this will not serve our purpose because in order to study the interaction between the nucleons, we need at least two nucleons. So we go for the next bigger system, which is another isotope of hydrogen, named as deuterium. The deuterium nucleus consists of one proton and one neutron. The nucleus of deuterium is called deuteron. Now let us proceed to find what information about nuclear force we can get from this deuteron. First of all, one important property of deuteron is to be remembered, that is, it always exists in its ground state and it has no excited state. What it means is that in case the deuteron is excited even to its first excited state, it no longer remains as a deuteron. Instead, it gets dissociated into its two component particles as independent particles. In other words, the first excited state of deuteron is an unbound state. Keep this information in mind, it will be required later. Right now, let us focus on its angular momentum. Since deuteron is composed of two particles, its angular momentum is the vector sum of the individual angular momentum of these two particles, one proton and one neutron. Each of these particles' angular momentum again has contributions from its orbital and spin motion. That is, the angular momentum of one particle is the vector sum of its orbital angular momentum and spin angular momentum. Mathematically, the angular momentum quantum number I for deuteron is the sum of angular momentum of its constituent proton and neutron. Again, total angular momentum of each of these particles is the vector sum of its orbital and spin angular momenta. Now recall at this point that the deuteron exists in its ground state. Hence, the orbital angular momentum quantum number L for both proton and neutron are assumed to be minimum value 0. Later on, there would be little modification to this assumption that we will discuss in appropriate moment. Since both L values are zeros, only the spins remain. Thus, the total angular momentum of deuteron is the vector sum of the spin angular momenta of two constituent particles. We know that the spin quantum numbers of both proton and neutron is half. Hence, the vector addition of these can have two values, 1 and 0. The vector addition is demonstrated with simple diagram here. Therefore, it is expected that when the angular momentum is measured experimentally, it would sometime correspond to the value 1 and sometime to 0. However, surprisingly, whenever the experiments are performed, the results correspond to I is equal to 1 always and I is equal to 0 never. This result shows with certainty that in deuteron, the spins of both the proton and neutron are always parallel and never antiparallel. Naturally, the question arises why these particles always have parallel and never antiparallel spins inside a deuteron. The answer is obvious. Deuteron with antiparallel spins of its constituent particles is not a bound system. That is why it does not exist. Whereas deuteron with parallel spins of its constituent particles is a bound system. And that is why it exists in nature. Now let us look at what makes a system bound or unbound. It is the total energy of the system. In case of a bound system, the total energy is negative. And for an unbound system, the total energy is positive. If we look at the energy scale for parallel spin system, total energy of deuteron is below zero level, and for antiparallel spin system, total energy is above zero level. So finally, we have arrived at the point that shows that the total energy of the system is depending on how the spins of the two particles are aligned, parallel or antiparallel. This implies that the force of interaction between these two particles, which is nuclear force, is spin dependent. This is something unique because the other two forces, electromagnetic and gravitational, have nothing to do with the spins of the particles. So for the first time, we have encountered a force that depends on the spin status of the particles. Now we will look into a direct implication of this phenomenon. Let us analyze two particle systems made up of proton and neutron. Utilizing these two particles, three combinations are possible. A two proton system called as diproton, a two neutron system called as dineutron, and a system containing one proton and one neutron known as deuteron. As we have just discussed, in order to form a stable bound system, the spins of both the particles have to be parallel, as in case of the deuteron. This makes the total energy of the system negative and thereby forming the bound system. However, in case of diproton and dineutron, since they contain the same type of particles, Pauli exclusion principle comes into play and prevents the particles having parallel spins, forcing them to have antiparallel spins only. As a consequence, both diproton and dineutron have total energy positive. That in turn makes both diproton and dineutron unbound systems. This explains why deuteron exists in nature while diproton and dineutron do not exist. In this way, by closely examining the two nucleon systems, we have established that nuclear force depends on the spins of the particles. We have also seen how this dependence on spin is responsible for the non-existence of diproton and dineutron in nature.